Oh, thank you very much. Thanks. Can you see my screen?
Yes, sir.
Yes, yes.
Yes,
Yeah,
sir.
yeah.
Screen and audio, video, and everything is fine.
Everything's fine. Okay. Thanks. Thanks a lot.
Yes.
Um, okay. So let me start by thanking the organizer for. Okay. Yeah. We'll start by thanking the organizer for giving me this chance to talk about our work. So I am at Indian Institute of Science, Bangalore, in the physics department. And so my background had been mostly, all the time, Hermitian, condensed matter theory. And so I got into non-Hermitian, and then now probably I'm not able to get out of it just because it's so rich and so interesting. So all these works were done when my postdoc Ananya Ghatak joined our group. And all the work I'm going to present today are done by her. She's now doing her another postdoc in Amsterdam. Okay, so I mean, we started with asking some basic questions on non-Hermitian system, especially on superconductivity. But slowly, once we started looking into topology and other quantum phenomena on these systems, we started digging more, and we started realizing that there are a few other things that we do not understand, and then we started trying to understand. Then we discover a few things. And one of the things that I'm going to emphasize today is, well, first of all, I will be talking about not in the entire quantum world, but only the PT symmetric system. And one of the puzzle that we started asking is that this mysterious C symmetry. So what is that symmetry? Is there any physical interpretation of that? So that was how we got motivated. And then we started digging into the small checks and all, and we realized that C symmetry might be actually an emergent gauge symmetry. And that gauge symmetry will emerge because we will find that without that, the theory is not gauge invariant. And yeah. And that gauge symmetry will be related to some conservation topological charge here. It's not necessarily a physical charge unless the gauge symmetry is externally arising, like with some magnetic field or constraints or other things. Then it could be related to your physical charge, but otherwise it could just be a topological charge. And then I will take one experiment to compare our hypothesis and figure out that indeed this is the hidden gauge symmetry that is arising in all these systems. And then we will be asking sort of the fun questions like what's the fate of those gauge symmetry to the spontaneous symmetry breaking? Like will they have Higgs modes and gap modes, and so we'll be asking that questions in terms of superconductivity that we started. So this is a review article which was mainly focused on non-Hermitian topological system. It was invited after 3-4 years of non-Hermitian topological. So there are already too many papers, 200, 300 papers we had to read and review. And we tried to review all the work that was done till then, but with one notations, one framework, one methodology, so that everything can be understood within basics that we develop in the gauge theory as well as in the Hermitian topological band theory. The other was some part of the work that I'm going to present is here, but some major part of it we are writing it. Okay. So with that, let me start. So let me start with this fun question that I think maybe centuries ago couple of centuries ago people had been asking, and that led to many interesting development, is like when we have this charged particle that acquires a dynamics, it gives rise to electromagnetic fields. So why fields adjust itself, but the charge of the particle, elementary particles are conserved? right? And that's sort of bucked many people, including as early as that we know is Lord Kelvin. He proposed that, okay, so atoms are nothing but a topological object such as knots, and because that time there was the hypothesis of ether and people are trying to understand or measure ether. There are a lot of interesting story, you can read it on Wikipedia, but I mean, Kelvin proposed that it's a topological object. And now we know that he was not actually too off, because now we have vortex, and we know that there is a topological charge which is the winding number associated with the vortex. So he was actually not off, but it's not the physical charge. And more serious proposal came from Paul Dirac, when he asked the same question, why electrons charge as quantized, and he proposed an experimental setup to test it out, which we know now is that Aronov bomb setup, in which he imposed a singular gauge by a vector potential, which is pure gauge, like without any magnetic field, in which the charged particle is moving. Then the single valuedness of the charged particle manifests that the charge quantization is related to monopole charge and vice versa. Okay, and we will actually be using this fact to show that the C symmetry is nothing but a gauge field with the topological charge in the P symmetry. And then the non-abelian part of those gauge field and the topology was introduced. Kulkarni, I think he has been credited, but around that time many people also did that. We know that to propose the elementary excitations of the quark have topological charge, which we call baryon number due to non-abelian gauge symmetry. Okay, so these are the set of questions we are also going to ask for PT symmetric case, and then we will have an answer, hopefully. Okay, so to begin with, I think this is a conference where everybody is already geared up with what is PT symmetric quantum theory. So I don't need to spend, but I will just start with only the PT part, which Carl Bender talked about, and our understanding or our way of looking at it, so that you can formulate the problem in the so you can see how we are formulating it in our language, but otherwise it's the same thing. So I mean, typically in quantum, when we build a quantum theory, we are looking into real observables, which we do not want to tamper with. Or any other formal or abstract object we define, we have the freedom to define in our way. But obviously it has to follow the proper quantum theory eventually. But in general, if you allow that flexibility, we do not have to stick to only any one definition, if you like, right? So the density, the probability density, and the energies can be written in terms of these two formal object, with psi being the wave function, and this is the conjugate of it. And again, the energies are the expectation value of operator, Hamiltonian operator, with this two states, two wave functions, right? But this operation can be replaced, as Bender pointed out, and followed by many people generalized with other formalism, but I'll just focus on here, in which the state itself has a symmetry in which it's got rotated, which is the PT symmetry. And since it's a space-time symmetry, the variables also are rotated, with the space rotated by parity, time rotated by a time reversal. And you replace these Dirac conjugations with this conjugation. Okay, and then the idea is that how do you develop the theory? That's the crux of the entire thing that we are after, right? So just compare with the Hermitian way. Just hermiticity itself is enough to ensure that in this formalism that the probability is unitary and the time evolution, unitary time evolution of the state is obtained by the Hamiltonian itself, right? So just hermiticity is good enough to obtain the theorem. But if you go to PT way, in which the Hamiltonian is PT symmetric, commutes, and the PT is +1, PT square is -1 will give trouble. And in one of our paper, we showed that how we can bypass that. But in general, if it's +1, then it gives you real eigenvalues. But it comes with challenges, and this is one of them. The probability, the inner product is not has a negative norm. And this was, if you go back to our undergrad math, the way we sort of solve it is we introduce this something called weight factor, and this is the C operator is kind of a weight factor, right? So then this inner product, if you substitute this one, it comes out to be C psi PT psi. So and we can go ahead and define CPT conjugate then PT. That's the definition. Okay, and so then we can call it CPT invariant system, and C is also a symmetry because it commutes to the Hamiltonian and it has the eigenvalues, which is just the -1 to the power n, some sort of a parity eigenvalues, if you like, or n is integer. Okay, so all your eigenstates are sort of enumerated with this -1. So it's a symmetry, but what symmetry it is there any physical one? We do not know. So that's our goal. So to motivate ourselves, so let's go back to how do we check the gauge symmetry of the system, right? So the way we check our gauge symmetry is for U1, if you give a local phase to psi n psi star with -1, then the inner product is, or the probability is, gets invariant, so there is no problem. But the Hamiltonian or the eigenvalues are not. The reason being, there is a Hamiltonian has a special dependence, gradients, and that gradients picks up a gradient of by this local gauge invariance, local gauge. So it's not a gauge invariant, but gauge covariant. But that term introduces energy contributions to it. And if you have magnetic field, the magnetic vector potential is also arbitrary with respect to this gradient of a scalar, so that absorbs it, and we have a local gauge invariant theory if you have a magnetic field. But without a magnetic field, so this field has to be constant, so that says that you can only have global gauge invariance, which is related to charge conservation, but no local gauge symmetry. But there is another one without magnetic field, which is the topology, where the gauge potential is a pure gauge, just coming from the gradient of a scalar potential. And you can impose these boundary conditions that as x goes to ±infinity in the thermodynamic limit, the psi goes to constant, but it just has a jump somewhere in between. So as it goes to constant, it doesn't add anything to the energy, but there will be a core energy where it changes sign. And then this will be singular, where it is sort of changing sign, or at some point, we can fix it to x equal to 0. This is a pure gauge because it doesn't have any magnetic field. The curl of a gradient is 0, right? And you can choose that point where it is singular is x equal to 0, or you can choose anywhere. And if your electron traverses a path without enclosing that gauge, then it's a simply connected path. So the wave function remains single valued, so it doesn't pick up any phase. But if the electron wraps around this monopole, then it picks up because it's so any phase is allowed, but the phase has to be integer because of the single valuedness. But otherwise it can pick up a phase. That's the Aharonov boundary phase, right? So here we can have a topological charge associated with the local gauge invariance. So if you test out the same thing for PT symmetric case, even at the inner product level, we have a problem. The reason being, here we define the inner product with with a non-local psi, because here psi is defined at a x space-time, but the psi, the conjugate is defined at a different space-time, right? So now if we give different gauge potential, which in principle one should be allowed like this, but then it's not a PT invariant case. Then obviously the Hamiltonian will also have the same. So there is no local gauge invariance even in the inner product. And also more generally we can ask this question is, this to psi, which is defined arbitrarily at any space-time, arbitrary with respect to a phase, then how do you make sure that how do you make sure that they have the same gauge? So we need a gauge fixing between this psi and that psi. And that's the answer. The C actually does the gauge fixing. It's like a parallel transport. So let's think of a space only here. Psi is defined here and psi pt is defined at some point. And we just choose it as a mirror in 2D. So we need to have a gauge fixing for psi and psi conjugate. And C does that job. How it does is that it's like a parallel transport. So you take this psi pt and then you want to bring it here with a parallel transporter, with a propagator, and then you have to integrate over x pt to x. So this integration goes, and that's how the psi cpt is defined, right? So what are the things that the parallel transporter should do? It has to make sure all the quantum numbers associated with psi remains same, right? So charge, spin, or any other quantum number should be the same, and also it should be path independent. It doesn't matter which path you take, right? So we can derive it. The way we can derive it is that we just give an infinitesimal translation, or translation. Let's start with, or like you're sort of defining with respect to x equal to 0 across the parity inversion, and do a Taylor series. So the first term is identity, which does nothing. The second term is the leading term. We can just go ahead and define it with a quantity del x as I Q A. So A is the connection, which does the gauge fixing, and Q is a global charge, which can be any charge, not necessarily physical charge. Okay. And then, so this is an infinitesimal transformation between these two. Then if there is a large one, then we can just go ahead and do it many times, as we always do for a continuous symmetry. And then you can exponentiate it, and this is what we get. Now you see, this is much like a chiral phase, right? Or an Aharonov-Bohm phase, with P being the path ordering. Yeah. So then it's a symmetry, right? It's a continuous symmetry. Yeah. So you can build it from an identity, and you can do it. And all these infinitesimally small transport are has the group property, right? And you can build a bigger transporter with small. So it's a symmetry. It follows all the symmetry principles. So now we will do two examples. Is that, let's take a psi as a single component complex field. So there's a U1 gauge, typically but instead of a U1 unitary, we will find out in a slowly that it should not be unitary, it should be UPT. I will define the UPT, but for the time being, it's just a single component U1. So the gauge field, the gauge connection can again be much like the Aharonov-Bohm effect, that it's a pure gauge without any magnetic field, and it should not contribute anything to the energy, so that this is the boundary condition. It goes to constant at plus minus infinity, like this, right? And it just changes sign at some point in between. It's like a soliton sort of a field, right? And wherever it goes through 0, it's a singular gauge. So any other gauge you can, so there is a still local gauge freedom, which makes it path independent. Is any other gauge which are not singular, you can gauge it out, but the singular gauge, you cannot gauge it out. That's what the gauge fixing is doing. And if I substitute this one here, it just depends on it doesn't depend on the path anymore. It just depends on the two values where you are taking the inner product, right? And then for the single valuedness of the wave function requires that this one has to be integer valued 2 pi n, and n is the winding number. So what it is doing physically is that as you take this state and parallel transport to here, the state can actually have an internal rotation or winding in its complex phase. You can see one phase. And how many times it winds is the winding number that it picks up. And this is exactly the value that Carl Bender also obtained. The C values or C eigenvalues are -1 to the power n. So what we have is all the eigenvalues, all the eigenstates of H are enumerated by the distinct winding number of the system. So all the states has to wind as you parallel transport. Even an odd will give you different phase, and that's what it accounts for the negative norm. Am I being too slow? Chair, can you just point me out? So should I speed up or?
Yes, there are 20 minutes left.
20 minutes left. Okay.
So you have half of your time you have already used.
Okay, thank you. Then we can go ahead and expand it for a degenerate state. Let's say there are n-fold degeneracies. So in general, we have a SUN symmetry, but here we will call it SUPT, which I have not yet defined, but I will define in a bit. And again, we go for a pure gauge, and here it will be defined by this. You can show that this is a pure gauge with curl being 0, and all these are matrix, which are matrix in the a matrix in whatever the symmetry we have. SUN value, the correspondingly algebra values. Okay, and then we can again substitute it, and you will find that the psi can be written as an answer with the generators of your SUN with the coefficient, and the coefficient has to satisfy the same boundary condition going from 0 to some value which will give you the integer winding. It can have many winding, depends on the form or the number of degeneracies you have actually. So yeah, and to see how this should look like, so omega is a function of the magnitude, so we sort of take it as a radial one, so that yeah. Yeah, so let's take a SUN manifold where you have 3 generators, so 3 components, this omega, and you can sort of think of it as going in the radial directions, omega. As the omega hits a value 2 pi n, this is where one of the winding in the SUN of the wave function that happens. And as it hits 4 pi, it winds another time, 6 pi, and it winds n number of times if there are n degeneracy. Okay, so that's how we think of it's like an onion, you know, it's like, yeah, every onion peels gives one winding. And then you can substitute these answers here, and then it's again -1. That's again what is done by Carl Bender. So let me now tell you what we meant by this SU, instead of a unitary, what we mean by SUPT. That's easy to figure out. Let's say the state is rotated in a degenerate case, is rotated by some matrix U, and what we want is the CPT inner product to be invariant under this rotation, right? Global rotation here. So this inner product invariance tells you that it's not the U dagger U, but it's U transpose CPT U has to be I. So that's the condition that U has to follow, and that's what we meant by SUPT rotation. or CPT if you like. Generalize. If C will usually come if it's a local rotation, right? And you can go ahead and check it in the Hamiltonian. So the time independent Hamiltonian had these eigenvalues, and the time dependent one, if we go ahead and try to check it, we do find that time dependence of the psi is not generated by just the Hamiltonian for the time independent one, but it's generated by Hamiltonian plus this gauge. You can work it out simply, and it turns out to be the same gauge that that we obtained here. Okay, so it's like a Hamiltonian plus gauge. It's like the dynamics of the system, the time dependence has generated this. It's like a very connection also. And then, I mean, either you put this gauge connection in the Hamiltonian or you put it here. It's a choice. It's a mathematical trick. So either you put it here and then keep the Hamiltonian to be same. There is just a gauge connection to your derivative term. And then all this gauge also has to also follow the same CPT rotation that we talked about. So then we can do a quick check with an experiment and see whether these sort of terms are indeed generated dynamically. You can take this example. I think some of the authors of this paper get a presentation here. So what is done here is you take a two-level system which are coupled by J, and one of the level is connected to a bath. Right? So this looks like a non-Hermitian system. It's a two-level system, and yeah, connected by this path. So and the observations of the system is that the eigenvalues and the energy and the probability both are real and unitary. This is unitary and this is real. So how do you understand this? First of all, this is not yet PT invariant. So what we can do is that here it makes much more sense not to invoke this this way of formulating it, but rather let's go and try to look at this formalism and see whether we can understand why these are real and unitary. So what we can do is that this is a generic non-Hermitian Hamiltonian. We can split it into a PT1 and anti-PT1. But you can show that this is also anti, because these are the generators of a symmetry. And generators of a symmetry, we know that it's anti-Hermitian. So it just turns out that this anti-Hermitian will be obtained by this. The C symmetry will actually be obtained by this. So then this Hamiltonian is PT invariant with the PT operator, which operates on the state, and the time reversal is generated by the complex conjugation, and this is PT invariant. The energy eigenvalues will be real as long as this criteria is satisfied, and in this criteria they do see unitary. Right? So then we can go ahead and calculate all the eigenvectors and try to check the PT invariant. It indeed comes up to be plus minus 1. And then the C operator of this system is 1 by E times H. So it's just the sign of the eigenvalues. Okay. And then CPT is plus 1. So because the system has particle symmetry, so it's sort of easy to show that it will always be, or it will be Hamiltonian. So that the minus eigenvalue will have minus norm, and plus eigenvalue will plus norm, and the C operator will have will fix that. Okay. And then you can go ahead and check this probability density, and indeed turns out to be the probability that comes from PT part is this, and from the anti-PT part will indeed embedded into these gauge connections from connected to the C operator. So this will be unitary, and as long as this is so this is like a Berry system, it will be dynamically generated, the system. And outside the PT symmetric PT broken region, this will be pick up a decay term. Okay, so it works whatever we proposed here. So in the last, I don't know, maybe 5 minutes or so, I will show you that we can ask all these fun questions like what's the field of this gauge field at the spontaneous symmetry breaking. And the spontaneous symmetry breaking we'll talk about here is a superconductor. So this was a fun project, not so much physically motivated, although there are plenty of reasons to study this. We discuss all this in the paper, but here is just a fun thing for us. Let's take a one band mean field BCS Hamiltonian with this kinetic energy term. And here you have two pair terms. It's a pair between two electrons, and this is a pair of two holes, and these are the gaps. So why do you want to take it Hermitian? Let's just keep them general. Delta tilde delta, and this will be the 2×2 Hamiltonian, and this will be the eigenvalues. So then we are interested in the real eigenvalues, right? So we can ask what are the conditions, and this is already real. So we just have to figure out what are the conditions on these two gaps which will give us real. Going to the polar coordinate, again defining theta to be arbitrary here. So this is the one which this term is real, so the amplitude, and this is the phase, and we want this term to be only pure real. So real eigenvalues that are obtained under the condition that theta plus theta tilde is in pi, n is integer. So for n even, theta is minus theta. You can just take it n equal to 0, then you can show that. So this is a Hermitian. And you have these eigenvalues which are always real. What we are interested here is in odd. So that means theta and theta, so the pair of electron pair and hole pair has a phase difference of pi and 3 pi and so on. Then you can have an anti-Hermitian, and then you will have eigenvalues which are real as long as the kinetic energy term is larger than the gap term. So this is the unbroken paired region, and the pairing is prohibited as long as the PT symmetry is broken, or pairing can be there can be decay. So if I think of a case space Brillouin zone, and I just chose some cartoon Fermi surface, then we can see that the pairing will happen everywhere else in the Brillouin zone except around the Fermi level, because this is where the PT will be broken. So there will be a Fermi surface of the Cooper pair. So these are the predictions. There will be a coexistence of pair and unpaired case space. It's a finite energy pairing. There will be superconducting Fermi surface. And another interesting difference we found is that the phase transition turns out to be first order, whereas it was second order for a Hermitian case. So to do that, let's just take a GINZBURG-LANDAU descriptions with this order parameter delta and delta tilde, and all these terms are allowed. These are the coefficients which depends on these potentials and the kinetic energy, so we just keep them to be same. So we just keep them to be same and check how things differ as you go from Hermitian to non-Hermitian. Okay. And this is the free energy as a function of delta. So for Hermitian case, so it's a dagger. So this one is just the amplitude of the superconductivity. So if we plug it in here, this is the theory we get, and we get a phase transition below Tc when A changes sign. This is the standard thing, right? When A changes sign, you have a phase transition, and you get a potential which minima shifts to some finite value of delta. So that's the second order phase transition. But when you have non-Hermitian pair or anti-Hermitian, that's the only allowed solutions here, you get a negative sign even to begin with from here. So now you can have a phase transition even when A is positive, or if you want to keep the same condition as Hermitian case, so A goes to negative, so this one will become positive. So you need to have a minus term generated from higher term. So this term is negative. So you can play with it, and you can show that for negative A, the only solution that is allowed is a first order phase transition. That is also consistent with the mean field solution, which I didn't show. So that there will be first order phase transition. Right. So now I'm sort of done. So now you can sort of make this and see what happened to the Meissner effect. Like you allow some gauge, but here we already have a gauge term because of the local gauge invariance of the system. So we just add a kinetic energy term with covariant derivatives. But the covariant derivatives has to make sure, I mean, it changes as the charge of the field that is associated with changes, right? So here this is for electron, this is for whole pair. So then they have to also have the opposite sign because the charge of the quasi-particle has changed. So with this, and here the gauge fields are the gauge field that we work it out from the C symmetry, right? Then you can just test out what happens to the Higgs mode. And we again use the same gap and the delta term with -1. And then what we find, it does give you a, so all these photons are now gapped with gap coming from the same amplitude mode. I mean, we get the same result as we would expect for the Hermitian case. And I was a little bit worried whether we'll get a negative mass, but thankfully because of the parallel transport as well as there is a negative sign here, these two negative sign, this two opposite sign makes sure that the photon gets positive mass. So we have a consistent theory. Okay, so I'm done. So we'll get a Higgs mass and Meissner effect even without a magnetic field. Okay. So these are my conclusions. So PT symmetric quantum mechanics has an emergent gauge, or if you want to realize such a system, you need to have a gauge field, which can be magnetic field or gauge potential with constraint with optical lattice and so on. And what also we talked about not the unitary rotation but SU-PT or UPT. Eigenstates are enumerated by the topological invariants, and static solutions obtained by PT symmetric Hamiltonian, whereas the dynamic solutions is defined by Hamiltonian plus a gauge field, which is a pure gauge, and spontaneous symmetry breaking will gap out those modes. So with that, I'm done. Thank you very much for your attention.
Yeah, thank you very much for your very interesting talk. Maybe I can ask just the first question. Did you compare your findings with usual Wilson loop techniques from QCD, for instance? And because your C transformations, when you have this gauge C transformation, it looks very much like just a cut by the half of the Wilson loop. Something like this.
Can you repeat, like the QCD, which I missed the keyword that you said. In the QCD, which one you want me to check with?
No, for instance, Wilson loop techniques, because your path ordered, when you're considering this C transformation here, from one half to the other, just you can think about it, just Wilson loop cut in the middle, and you have half a Wilson loop actually. Did you compare this with some findings?
I have not yet, but I think these are similar to what we are doing here.
Yeah, sure. Yes.
And in fact, the QCD one, this is what the sort of invariance they do. And as I wanted to, because you also mentioned QCD, so I just wanted to show that all these winding number that we got here are the baryon numbers in the QCD.
Oh, okay. Thank you. Are there other questions?
Could I have a question?
Yeah, sure.
It's really amazing how nicely one can formulate this type of gauge symmetry in PT symmetry context. What I would suggest is that one could make a next step by returning to the more general situation in which there is no PT symmetry and in which one has this quasi-Hermitian formalism in which instead of C operators, there may be other independent observables which don't have these features of symmetry. And my question is whether one could still formulate this differential geometry and covariant derivative approach to formulation of the final, so to say, unique formulation of the theory.
I mean, yeah, you are asking, you are giving me a project and which also we have thought about. For example, our next one would be to look into the pseudo-Hermitian one, and then we like to see. I mean, I do have some idea, which since we are sort of quite behind in the project, I didn't want to sort of speculate all the answers. But I think we can formulate in the pseudo Hermitian case.
Okay, it's thank you. It's,
Yeah, I mean, we can discuss that separately.
It's very good to hear that,
just
that
didn't
you
want
are
to-
going to continue along these lines. Yes, thank
Yes,
you.
yes. I will do that.
Can-
Yeah, thank you.
can
Other
I-
questions?
Yeah, can I have a question?
Yes,
Yeah,
Bhabani.
sure.
Tanmoy, I didn't get how the anti-PT symmetry comes in the picture. It's coming because of some principle, or it happens to be that baric phase is related to the anti-PT Hamiltonian.
I did go a little fast, and few things. I mean, in this particular example, I mean, it's a very good question, because you take any. I mean, our goal is to show that you take any Hermitian, any non-Hermitian Hamiltonian, you break it into PT, and then you develop the theory. The anti-PT one will turn out to give you the C operator. So that's the conjecture, but I have not yet, I mean, that's the hope that it will be, but we have not yet proved that.
Okay.
In this particular example, it turns out to be the case.
Okay, I got it. So this,
As an example, I see that it works.
yeah, okay.
But in general, this is the kind of thing. Can you still follow my pointer?
Yeah, sure.
So I was like, in future, I'm after with any Q is your generic Hamiltonian, then you break it into a PT1, and whatever you have the anti-PT1 can be written in terms of a C operator, and show that that is exactly the C operator you will get.
So at present, it is supported by only this example, or you have more examples? Okay.
No, in the no, two more examples. The other one is there in our paper,
The
which I
supersymmetry. Yeah, sorry, superconducting.
No. The first one I showed. Let me see. This one.
Oh, okay.
There is another example. Actually, there might be a couple more examples in this review also.
Okay.
But the general
Okay.
proof is still missing.
Yeah,
I wish I
yeah.
could do that.
Yeah, I'm curious about that. Yeah.
Maybe we can discuss. Yeah.
Yeah, okay.
Okay, some other questions, or maybe they could be posed privately afterwards.
Sure.
Okay, in this case, let's thank again the speaker for the very interesting talk and discussion, and we may pass to the next speaker.